The next question is a very simple question. Just the basic understanding of Wien's displacement law and a bit of mathematical knowledge. And you are done. The question is, which of the following graphs correctly represents the variation of log of lambda m with log of t, where lambda m is the wavelength corresponding to maximum intensity of radiation and T represents the absolute temperature of the body. So the given graphs are these four. In these graphs, you have to select which graph is correct representation of log of lambda m versus log of T. As per the Wien's displacement law for a black body, you know that lambda m into T is equal to B, where B is the Wien's constant, right? And lambda m is the wavelength corresponding to the maximum intensity of radiation. T is the temperature at which the graph is being plotted, right? Okay. Now, to this equation, if we take log on both the sides, so log of lambda m into T is equal to log of B, right? B is a constant, so log B will also a constant, right? The lambda m varies with temperature, right? So in this case, if we just separate out lambda m and T, it will be log of lambda m plus log of T is equal to log of B, right? We can take log of lambda m on one side and we can write the equation as minus of log of T plus log of B, right? If you look into the equation, this equation you want in graphical format. Why? Because log of lambda m is something you want on y-axis and log of T is something you want on x-axis. So for the simplification, let me replace this log of lambda m with y. So this is nothing but y is equal to minus of log of T, which is x, plus log of B, that is a constant. So that will be plus a constant c, right? Y is equal to minus x plus c. Is it the equation of a line, of a straight line? Yes. Because for the straight line, you study the equation as y is equal to mx plus c. You are studying it from the class 7th or 8th, right? Y is equal to mx plus c, where m represents the slope and c is the constant, right? So if we plot y versus x over there, m is the slope. If you compare this equation, m comes out to be minus 1. So the slope is negative. So for the given data, the slope will be negative. For the given graph of log of lambda m versus log of T, the slope will be negative and it will be a straight line, right? This y is equal to minus x plus c. You want to plot? Okay. So at x is equal to 0, if you put x is equal to 0, the value of y is equal to c, right? So at x is equal to 0, the value of y is equal to c. That's a positive constant, log of b, right? If you compare this c as log of b. And at y is equal to 0, x is equal to c, right? So this y is equal to 0 gives me x is equal to c. So the line should be like this, right? The line should be like this, right? And y is what? Y is my log of lambda m and x is my log of t, right? So log of lambda m versus log of t will be a straight line with a negative slope. Let's look at the options. Option B will be the correct option in this case. Again, a simple problem based on the Wien's displacement law. The statement is the wavelength of maximum energy radiation released during an atomic explosion is 2.93 into 10 raised to power minus 10 meter. The corresponding temperature attained must be of the order of. Out of the given four, you have to select out the correct option. You have been given the value of Wien's constant, that is 2.93 into 10 raised to power minus 3 meter Kelvin, right? Okay, so the explosion takes place and what happens? The wavelength which is getting emitted for the maximum intensity is given by lambda is equal to 2.93 into 10 raised to power minus 10 meter. This is the wavelength corresponding to maximum intensity, right? The maximum number of photons are coming out with this wavelength. So is this lambda m? Yes. Lambda m in this case is given to be 2.93 into 10 raised to power minus 10 meter and you are supposed to get the temperature. You know, in the Wien's law, you have studied that lambda m into T is equal to Wien's constant B, right? So lambda m, which is 2.93 into 10 raised to power minus 10 meter into, let's say, the temperature, the order of temperature is T, must be equal to Wien's constant, which is 2.93 into 10 raised to power minus 3, right? Here, if you look, 2.93 gets cancelled by 2.93. 10 raised to power minus 10 multiplied by T comes out to be equal to 10 raised to power minus 3. So temperature comes out to be 10 raised to power minus 3 plus 10. That is 10 raised to power 7. So the order of temperature is 10 raised to power 7 Kelvin. That, if you match with the options, option B will be the correct option in this problem. Again, a problem based on the Stephen's law. I told you the 4 concepts you need to remember in this chapter, and every problem will come like from either of them, right? So this problem is the two bodies, a sphere and a cube, made of the same material and having the same volume, are heated to the same temperature and are allowed to cool in the same surrounding. The ratio of net radiant power in both will be, right? So let's look into the figure. These are the two bodies, the sphere and the cube. Given to you, they are heated up to the same temperature, let's say T. So T will be the temperature of both of them, right? For our assumption, let's say the radius of this sphere is R and the side length of this cube is A. A is the value of each side of the cube, right? Okay. They are kept in the same surrounding. So they are kept in the same surrounding. Let's suppose that surrounding is having a temperature Ts, where let's say T is greater than Ts, because they are allowed to cool down. They will cool down only if they are having the temperature greater than the surrounding, right? So from the question it is clear that T is greater than Ts, right? T is the temperature of the bodies. Stephen's law says that every body which is having a temperature greater than 0 Kelvin will emit the power at a rate of, or will emit the heat energy at a rate given by dq by dt is equal to sigma E. E is the emissivity into A is the exposed surface area into T body power 4. But that is just the contribution of emission, right? If you want to get net rate of emission, you have to subtract whatever is being absorbed, right? So in order to take care of that term, we take this minus Ts power 4, that is minus T surrounding power 4. Now if you see this, the first term, which is sigma E sigma A T power 4, that is the rate at which the body is emitting the heat, right? Minus the second term, if you see, E sigma A T surrounding power 4. This is the term which is corresponding to the absorbed rate of energy, or rate of absorbing the energy, right? So in total, this gives you dq by dt net. That is the net rate at which the body loses out the energy, right? And the ratio of dq by dt for both the bodies is supposed to be calculated. For the sphere and for the cube, you are supposed to calculate dq by dt net, the ratio of dq by dt net, right? Let's suppose dq by dt, for the simplicity, I am denoting by E. So basically what you want E sphere divided by E cube is what, right? This is what you want. This is what you want to calculate. And from the Stephen's law, you need to understand that the formula for dq by dt net is given by this above written formula, right? Or okay. Now let's calculate E cube or E sphere divided by E cube. Sphere was the first body, so E1 by E2 is E sphere by E cube. That will be given by emissivity of the material. Emissivity is the property of material. They have the same material, so the emissivity for both of them will be same. Multiplied by surface area of sphere, multiplied by, tell me, multiplied by Stephen's constant, multiplied by temperature of the body minus temperature of surrounding power 4, right? Divided by emissivity of cube, again the same material, the material is given to be same, E, A of cube, that is the exposed surface area of the cube, into sigma into T power 4 minus Ts power 4. if you simply look into the expression, everything gets cancelled from up and down. Only the surface area, the exposed surface area of both the bodies remain into the picture. So E sphere divided by E cube will be given by surface area of the sphere divided by surface area of the cube, right? And the surface area of the sphere is equal to 4 pi small r square. Small r is the radius, I have assumed, right? Divided by a cube is the total surface area of the cube. So the cube is having 6 surfaces, each of radius, each of surface area a square, right? So the total surface area for the cube will be 6a square, right? Basically, you have to get a and r, the relation between a and r, to figure out what this ratio is equal to, right? So in order to figure out what is the relation between r and a, what is given? That the volume of both of them is equal, right? So the volume of a sphere is 4 by 3 pi r cube, and that is given equal to the volume of cube, that is a cube, right? So from there I can write a is equal to 4 by 3 times pi power 1 by 3 multiplied by r power 3 power 1 by 3, that becomes r, right? So the a square, the value of a square will be 4 pi by 3 power 2 by 3 into r square, right? And this a square I want to put in this. So this becomes equal to 4 pi r square divided by, okay, please follow me, 6 times a square. A square will be 4 pi by 3 power 2 by 3 multiplied by r square. This you just need to solve, right? A bit of mathematics. R square gets cancelled, and then this becomes equal to, see this 2 2 ja 4, 2 3 ja 6. This becomes equal to 2 pi by 3 multiplied by, just follow me, please do not lose the focus, multiplied by 3 times, okay, this 4 pi by 3 I'll first square and then put 1 by 3. So 4 by 3 square becomes 16 by 9 whole to 1 by 3, and this pi becomes pi power 2 by 3, right? This pi power 1 and pi power 2 by 3. Pi power 2 by 3 goes up, it becomes pi power 1 by 3, right? So this will be equal to, see this 2 by 3 I want to write in terms of power 1 by 3. So I can write 8 by 27 power 1 by 3, right? 2 by 3 I can write as 8 by 27 power 1 by 3, right? Multiplied by this 16 by 9 I'll take as 9 by 16. 1 by 16 by 9 I'll take at 9 by 16, and this is having again a power 1 by 3. And this pi power 1 divided by pi power 2 by 3 becomes pi power 1 minus 2 by 3, that becomes pi power 1 by 3. This if you see, 8 1 ja 8, 8 2 ja 16, 9 1 ja 9, 9 3 ja 27, right? So this becomes 1 into 1 power 1 by 3, that is 1. So this becomes 1 multiplied by pi power 1 by 3 divided by 3 into 2, that is 6 power 1 by 3, right? So E1 by E2, that is E sphere by E cube, is given by the ratio pi by 6 power 1 by 3. So E sphere is to E cube, the ratio is equal to pi by 6 power 1 by 3 ratio 1, right? Let's look at the options. Pi by 6 power 1 by 3 ratio 1, that is option C, and that will be my correct option in this case. Again, a similar problem as the previous one. All the formulas which you used in the previous problem is to be used in this problem as well. Only the data which is being asked is slightly different, right? So the question is, the power radiated by a black body is P naught, and the wavelength corresponding to the maximum energy is lambda naught. On changing the temperature of the black body, it was observed that the power radiated becomes 256 by 81 times P naught. The shift in the wavelength corresponding to the maximum energy will be. Now, why will the wavelength shift? Because the temperature is being changed, right? Because as you change the temperature, the wavelength corresponding to the maximum energy gets shifted, right? Because I know that lambda m times T is equal to B. This is my Wien's displacement law, right? So if you change temperature, the wavelength corresponding to the maximum energy intensity will also change, right? Okay. Now the temperature is being changed, but the related power change is given to you. Not the temperature change is given to you. The temperature change is not given to you, right? What is given to you? How the power changes, right? Okay. So can the power formula be related with temperature? Yes. Power formula is given in terms of the temperature of the body by Stephen's law, right? So this is the body which is given to you, which is emitting some power P naught. The wavelength corresponding to the maximum energy is lambda naught. Let's say the temperature is T naught. The initial temperature of the body is T naught. And let's say the temperature is changed from T naught to a value T. So the body emits the power at a rate of 256 by 81 P naught, right? Emits the energy at a rate of 256 by 81 P naught. You have to get what is the wavelength corresponding to the maximum energy that, let's say, is lambda, right? Let's say the lambda m changes or lambda naught changes to lambda, right? Okay. Now, Stephen's law says that the power emitted by a black body is given by A sigma T power 4. A is the exposed surface area of the body, sigma is the Stephen's constant, and T is the absolute temperature, right? This is the total power or the total heat or the total radiation emitted by the body per unit time, right? By the black body per unit time. Now from the case 1, or this is the case 1, if you apply the formula, you can write P naught is the power emitted given by A sigma. A, let's say, is the area of the body. Sigma into T is T naught, that is T naught power 4, right? That's the equation number 1, you can say. And the same formula you can apply for case 2. You will write power changes to 256 P naught by 81. That must be equal to A sigma T changes, temperature changes to T power 4. That's equation number 2. Equation number 2 divided by equation number 1 will give you 2 divided by 1. That will give you 256 by 81 is equal to T power 4 divided by T naught power 4, right? And since I know lambda m into T is equal to constant, so the ratio in the temperatures in the two state will be equal to the inverse ratio of the wavelengths, right? Lambda m is proportional to 1 by T, right? So I can write the final temperature by initial temperature is equal to the initial wavelength by the final wavelength, right? Wavelength, where wavelength is corresponding to the maximum energy, right? Maximum energy. That's the logic. Okay, so this I can write as lambda naught by lambda power 4, right? And this 256 by 81, is that 4 by 3 whole to the power 4? Yes. So what I can write is 4 by 3 whole to the power 4 can be written equal to this. That is lambda naught by lambda whole to the power 4, right? This gives you lambda naught by lambda will be equal to 4 by 3. This gives you lambda is equal to 3 by 4 lambda naught. What you are supposed to ask is a shift in the wavelength. Shift means the change in the wavelength with its magnitude. Either the wavelength is increasing or decreasing, the shift is a positive number, right? Like it's a positive quantity, right? Whether it increases by some amount or decreases by some amount, that amount is basically the shift, right? So it's the magnitude of delta lambda. So that is the magnitude of lambda final minus lambda initial, right? And lambda final, as you know, is 3 by 4 lambda initial. So this I will write as magnitude of 3 by 4 lambda naught minus lambda naught. So shift, that is delta lambda, that is the magnitude of delta lambda, becomes lambda naught by 4. So the shift in the wavelength, becomes equal to lambda naught by 4. Let's check the options. Option A will be the correct option in this case. Very simple problem. From the statement, it will be clear that what is the answer. A certain substance emits only the wavelengths lambda 1, lambda 2, lambda 3 and lambda 4 when it is at a higher temperature or at a high temperature. when the substance is at lower temperature, it will absorb which of the following wavelengths? So if you remember the Kirchhoff law says E is equal to A, right? Where E is the emissivity, and A is the absorptive power, right? E is equal to A. What this equation physically means is a good emitter is a good absorber, right? So a body, this you must have studied in the Kirchhoff law section in your theory sessions, that a body which is emitting a certain wavelength range at a higher temperature, if it is kept at a lower temperature, it will absorb those wavelengths at the lower temperature. A good emitter is a good absorber, right? Good emitter is a good absorber. So if a body at a higher temperature, if it emits like certain wavelengths, let's say lambda 1, lambda 2, lambda 3 and lambda 4, if it emits them at a higher temperature, then if the temperature of the body is low, then it will absorb the same wavelength range, lambda 1, lambda 2, lambda 3 and lambda 4. So the answer to this problem will be option D, that is, it will absorb all the wavelengths spectrum which is it was emitting at the higher temperatures. So it will absorb everything which is lambda 1, lambda 2, lambda 3 and lambda 4. So option D will be the correct option in this case.